In this problem, we're asked to determine the moment of the force F about point O. We're given the magnitude of F as well as the coordinate direction angles of F. We're asked to express the result as a Cartesian vector. So as discussed in the lecture, when we have a moment problem in 3D space where we're asked to find the moment of a force about some point in 3D space, we're going to use the equation the moment is equal to r cross F. It's a vector equation. And where r is any position vector between the point that we're finding the moment about and the line of action of the force. So in our problem, r is going to be from O to the line, somewhere along the line of action of the force F. So let's focus on r first. Here's the line of action of F. And the only point on F that we know anything about is right here at the end of the pipe assembly where F is applied. And we'll call that point C. And while we're here, we will write down the XYZ coordinates of C, which are X 0.4 meters, Y 0.5 meters, and Z 0.3 meters in the negative direction. It's going to be negative 0.3. Now the position vector from from O to C is here. Call that R sub OC. And now we have everything we need to write R sub OC in Cartesian form. Before we do that, it's pretty obvious that R sub OC is the best position vector to use in this problem. We probably could find the coordinates of other points along the line of action of F, given the information that we have, but the math would be prohibitive. We want to pick the easiest legitimate way to do the problem, and R sub OC is the position vector that makes sense. Okay, so we'll call this R sub OC, and we know that a position vector in Cartesian form can be expressed as the difference in the x coordinate of C and the x coordinate of O, plus the difference in the y coordinates, plus the difference in the z coordinates. Remember that the position vector has to be from O to C, and that the coordinates of C will show up first in these calculations. In other words, what's the difference between C and O? If you get these flipped, you're going to have problems. So we can simplify that and write that R sub OC is 0.4i plus 0.5j minus 0.3k. So we have R. Now we need F. F is going to equal the magnitude that we were given times the cosines of the coordinate direction angles. It would be cosine 60 degrees I. Yep. Okay, that'll fix that. Times plus the cosine of 120 degrees J plus the cosine of 45 degrees K. Okay, and we expand that and we'll get 800 times the cosine of 60, which is 0.5, is 400 I. 800 times the cosine of 120 degrees, which is negative 0.5. So this will be minus 400j. And 800 times the cosine of 45, which is 0.707. So this one will be, the k component will be 565.7k. You're storing all these numbers in your calculator to keep the accuracy of those numbers, those intermediate calculations, as high as possible and not rounding until you get to the final answer, just like in all of our previous problems. Okay, so we have F. Now we can write moment about O equals R sub OC cross F, and we can now put that cross product, since we have the two vectors in Cartesian form, into a determinant. Where the first row is going to be ijk. The second row is going to be the magnitudes of the ij and k components of our position vector, 0.4, 0.5, negative 0.3. And the third row is going to be the magnitudes of the ij and k components of our force, which are 400 minus 400, 565.7. Okay, let me move the screen up a little bit so I have room here. Okay. So now I'm going to expand that determinant. I'll just go ahead and write this over again. So the moment about O equals R sub OC cross F, which equals, and I'm going to put the three components ij and k on separate lines just to try and keep it a little bit organized. Okay, So the I term, let's start with a big bracket. I'll show the details of calculating the I term, and then I'll not show the details of the J and K term. So to calculate the I term in the 3 by 3 determinant, we cross out the row that the I is in and the column that the I is in, and then we're going to multiply the 0.5 by the 565.7, and then we're going to subtract the negative 0.3 times the 400. And all that will be times I. So we're going to have 0.5 times 565.7 minus negative 0.3, you got to be careful with the minus signs, times a negative 400. I. Now the J term, we know from the lecture, has a negative sign in front of it. And the J term is going to be 0.4 times 565.7 minus negative 0.3 times positive 400 J, and the K term is going to be plus 0.4 times negative 400 minus 0.5 times 400 K. So now we do that math for each component, and we end up with $163I minus 346J minus 360K. Now they ask for the answer in Cartesian form, which is what this is, and don't forget the units. We were working in newtons and meters, so this moment is in Newton meters. That's the final answer.